Hello everyone, welcome to the lecture again. In the last class, we learned about the definition of moment of inertia of some standard bodies, the parallel axis theorem and the perpendicular axis theorem. Today, we are going to utilize those concepts and going to solve some examples wherein we will find the moment of inertia. So, this is the first problem statement. The upper edge of the thin homogeneous plate of mass m is parabolic with a vertical slope at the origin O. Determine its mass moment of inertia about the x, y and z axis. Okay. So, here we have this x axis, y axis and the z axis. We have this plate which is parabolic. Okay. It has a thickness of T. So, T is the thickness and the height is h. So, to find out the moment of inertia, let us take a portion of this plate, okay, which is rectangular in shape. Let us say it is at a distance of x and the width of this plate is dx. Okay. So, from the equation, because this is the equation of the parabola, we know that how x varies as a function of y. So, this will be x equal to some constant into y square. Now, this constant also we can find out from the boundary condition. It is given that if x is equal to b, then y becomes h. Okay. So, at x equal to b, we have y equal to h. Let us put it over here. So, we have b equal to constant into h square and this gives that constant equal to b over h square. So, let us put it above. So, we get x equal to b over h square y square or y equal to h over square root b square root x. So, this is how y and x varies. Let us call it equation number 1. Now, let us say that the mass per unit volume of this plate is rho, okay, and let us find out then what will be the mass of this object. Okay. So, let us say that rho is the mass per unit volume of the plate. Okay. Then total mass m will be integral dm. Now, if the mass per unit volume is rho, then we have to multiply this rho by the volume to get the mass. So, the volume of this plate will be T times y into dx. Okay, because y dx is the area, T is the thickness. So, you multiply this to get the volume and then multiply by rho to get the mass. Okay. So, therefore, mass m will be rho is constant, T is also constant. and let us write down this y in terms of x to find out this integral. So, the value of y I can put from equation number 1, it is h over square root b x to the power half dx, okay, and this will be equal to rho t h over square root b x to the power 3 by 2 divided by 3 by 2, and then we have to put the limit of the x. X varies from 0 to b, okay. Therefore, m is equal to 2 by 3 rho t h b, okay. Let us call this equation number 2. So, now we have the mass. Let us find out what is the moment of inertia about the x axis first, okay. So, about the x axis I am writing it as I x x, that means the moment of inertia about the x axis. So, to find out the moment of inertia of the x axis, we have to find out what is the moment of inertia of this part. About the x axis, okay. Now, this is a rod, and we have in the last class we have find out what is the moment of inertia of a rod about one end, okay. So, there we can use the parallel axis theorem. We know the moment of inertia about this point is ml square divided by 12 and then m h by 2 whole square, okay. So, let me just remind you. So, the moment of inertia about this line was m l square divided by 12 plus m x square. So, m x is here h by 2 whole square. So, this will also be h because there is no L, there is h only. So, this will give you m L square divided by 3. So, herein we have used the parallel axis theorem. This is the moment of inertia of this part about the x axis, okay. So, let me write it down. So, it will be 1 by 3 integral, here it will be y square into dm, okay. So, 1 by 3 is this factor, L square we have y here because there is no fixed L, it varies as a function of x according to the equation of the parabola. So, it will be y square and then in place of m we have dm, okay. Now, let us find out this, it will be 1 by 3 integral y square dm, okay. Dm we already know, dm is this quantity rho t y dx, okay. So, here rho and t and 3 they are constant, let me take it outside, y to the power 3 dx, and this will be rho t h to the power 3 divided by 3 b 3 half integral x to the power 3 by 2 dx. So, what I have done is from equation number 1 I have put the value of y. Now, this integral we can find out the limit of the x is gain from 0 to b. So, this comes out to be rho t h to the power 3 divided by 3 b 3 by 2 x to the power 5 by 2 divided by 5 by 2, limit is 0 to b. So, this gives you 2 by 15 rho t h to the power 3. So, this is the answer. Note that here in the question statement rho is not given, the mass is given. So, this value of rho also I can put from equation number 2, okay. So, I can eliminate rho in terms of m from equation number 2. So, if you do that then you get I x x equal to 1 by 5 m h square. Okay. Now, let us find out the moment of inertia about the y axis. So, I y will be integral dm x square, okay. So, this will be integral x square dm I can put from here, it is rho t y dx. So, this will be rho t y is h over square root b square root x. So, h over square root b and x square root x dx. Okay. So, this will be rho t h over square root b x to the power 7 by 2 divided by 7 by 2 and the limit will be from 0 to b. So, this will be 2 by 7 rho t h over square root b to the power 7 by 2 which is equal to 2 by 7 rho t h b to the power 3. Now, again here I have rho, the value of rho I can put from equation number 2. So, rho is 3m divided by 2 t h b. Okay. So, let me put it over here. So, this is equal to 2 by 7 t h b cube and then the value of rho was 3m over 2 t h b. Okay. So, t will get cancelled, h will also get cancelled and we will have 3 b square m divided by 7. Okay. So, this is the moment of inertia about the y axis. Now, let us look at the moment of inertia about the z axis. Now, note that this plate it lies in the xy plane. Therefore, the moment of inertia about the z axis will be the sum of the moment of inertia about the x and the y axis. Okay. So, for thin plate which lies in xy plane, the moment of inertia about the z axis will be the moment of inertia about the x axis plus the moment of inertia about the y axis. So, the moment of inertia about the x axis was 1 by 5 mh square plus Iyy was 3 by 7 mb square. Okay. Now, let us look at another problem. Determine the moment of inertia of a right circular cone with respect to A, its longitudinal axis, B, an axis through the apex of the cone, and perpendicular to its longitudinal axis. And C, an axis through the centroid of the cone and perpendicular to its longitudinal axis. Okay. So, herein we can clearly see that how a cone is formed. A cone can be realized by revolving y equal to kx line about the x coordinate. Okay. So, for example, I have the axis x and y, and if I have y equal to kx line, you rotate it about the x axis, then you get the cone. Okay. So, you have the x axis the y axis and the z axis, you have a line, let us say y equal to kx, you rotate it about the x axis and you will get this cone. Herein the boundary conditions are given that the height of the cone is h and its radius is a. Okay. So, therefore, I can find out what is the value of k, because here at x equal to h, y should be a. Okay. So, at x equal to h, y is equal to a, therefore, a equal to k times h and therefore, k is a divided by h. So, therefore, we have the equation of the line that form the cone and it is y equal to a by h into x. Let us call it equation number 1. Now, to find out the moment of inertia of this, we have to look for the symmetry, and clearly there is axial symmetry. So, therefore, let us choose a disc and let us say at some x its diameter is 2y or radius is y, okay, and the thickness of the disc is dx. Okay. So, as I said, because there is a axial symmetry, I choose disc shape slice. Okay. Now, let us find out what is the moment of inertia of this disc, and then we will integrate it from 0 to x, which is h here. So, the mass of this element dm is the density times the volume. So, density is let us say rho and the volume is area multiplied by the thickness. So, area is pi y square dx. Okay. Therefore, the mass m will be integral dm, which is equal to 0 to h rho pi y square dx. Okay. And this integral I can find out. So, for that let me first put the value of y. So, I will have integral 0 to h rho pi and y square is a square over h square x square dx. Okay. So, therefore, m is rho pi a square over h square into x to the power 3 divided by 3 and the limit is 0 to h. Therefore, m is equal to rho pi a square h divided by 3. Let me call it equation number 2. Now, the first part we have to find out the moment of inertia about the longitudinal axis, which is the x axis here. So, I x x, it will be integral moment of inertia of this disc about the x axis is half m y square. So, it will be half dm y square, okay, because the mass is dm. So, let me put the value. So, it is half dm, we know it is rho pi y square dx. So, rho pi y square is a square over h square x square and dx. So, this is my dm into y square is a square over h square x square, okay, and the limit on x is 0 to h. So, this I can rewrite as half rho pi a to the power 4 over h to the power 4 integral 0 to h x to the power 4 dx, okay, and this integral is half rho pi a to the power 4 over h to the power 4 into x to the power 4 integral is x to the power 5 divided by 5. So, it will be h to the power 5 divided by 5 equal to 1 by 10 rho pi a to the power 4 h. So, this is the answer, but here I have rho I can replace with equation number 2. So, rho will be 3 m over pi a square h. So, this I can put it back. So, I get I x x equal to 1 by 10 and rho is 3 m over pi a square h into pi a to the power 4 h. Okay. So, this is equal to 3 by 10 m a square. Okay. Now, let us find out the moment of inertia about the y axis. Okay. So, let me make this figure again. We have the x axis, the y axis and the z axis. We have this cone and then we took this disc of thickness dx and its height was y and the radius of this cone at the end was a and this was h. Okay. So, this is the situation that we have. Now, we want to find out the moment of inertia about the y axis. So, to find out the moment of inertia about the y axis, I have to first find out what is the moment of inertia of this disc about this axis and then I can use the parallel axis theorem. Okay. So, the moment of inertia of this disc about this line is 1 by 4 dm y square. Okay. And plus we have to find out what is the moment of inertia about this axis. So, I have to add x square dm here because this distance is x. So, therefore, plus x square dm. So, note that here I have used the parallel axis theorem. So, this comes from the parallel axis theorem. Now, let us solve it. So, we have dm into y square is a over h into x whole square. So, we have by 4 also a over h into x square plus x square dm. Okay. So, this I can write it as integral dm is rho pi y square dx. So, rho pi y square is a over h into x square. So, let me take this dm outside. Okay. And then I have a square over 4 h square x square plus x square and then dx. Okay. So, I just put the value of dm here in terms of the rho. Okay. So, this I can solve now. It is rho pi a square over h square, all these are constant, then the limit on the x is 0 to h, a square over 4 h square x to the power 4 plus x to the power 4 dx and this will be rho pi a square over h square, a square over 4 h square into x to the power 5 divided by 5 plus x to the power 5 divided by 5 and the limit is from 0 to h and this will be equal to rho pi a square over h square, a square over 4 h square plus 1 into h to the power 5 divided by 5. Now, again this value of rho I can write down in terms of m. So, let us do that. So, it will be rho is 3 m over pi a square h. So, 3 m over pi a square h into pi a square divided by h square and then rest of them. So, I can write down this bracket as a square divided by 4 plus h square divided by h square. So, this is just simplification, h to the power 5 divided by 5. Now, this h square and h will get cancelled with h to the power 5. So, we get 3 by 5 m into a square divided by 4 plus h square. Okay. This is the moment of inertia about the y axis. In the third part, so part C, we have been asked to find out the moment of inertia through the centroid, okay, which is perpendicular to the longitudinal axis. So, that means we have to find out the moment of inertia. So, this was x axis, y axis and the z axis. We have this cone and we have to find out its moment of inertia about the centroid, which is perpendicular to the longitudinal axis. Okay. So, we have to find out the moment of inertia about this red line. So, note that the centroid in the cone is situated at a distance of 3 h divided by 4 if h is the height of the cone. Okay. Now, to find out this moment of inertia, we can use the parallel axis theorem, because we have already calculated what is the moment of inertia about the y axis. So, the moment of inertia about the y axis is the moment of inertia about this red line. So, let us call it I y bar plus m into the distance. So, x bar square. Okay. So, all of them we know. So, I y will be I y minus m x bar square. So, let us put the value, it is 3 by 5 m a square divided by 4 plus h square minus m x bar is 3 h divided by 4 whole square. So, that comes out to be 3 by 20 m a square plus 3 by 5 m h square minus 9 by 16 m h square, and this we can write as 3 by 20 m into a square plus 1 by 4 h square. Okay. So, this is the answer. Now, let us look at one more problem. The radius of the homogeneous solid of revolution is proportional to the square of its x coordinate if the mass of the body is m. Determine its mass moment of inertia about the x and y axis. In this question, it is given that the y varies as the square of the x coordinate. So, let us take y equal to k x square, and k I can find out from the boundary condition. Okay. It is given that at x equal to h, y is equal to r. Let us put it in the equation. So, we have r equal to k h square, therefore, k is equal to r over h square. So, if I put it over here, then I get y equal to r over h square x square. Let us call this equation number 1. This tells me how y varies as a function of x. Now, to find out the moment of inertia of this, I have to choose some element, and because of the axial symmetry, so this structure is symmetrical about the x axis, therefore, let us choose disc shape slice. Okay. And the mass of this element will be let us call it dm. So, that will be again the rho times the volume, and the volume will be dx times the area, which is pi y square. Okay. Therefore, the total mass of this object will be integral dm equal to integral 0 to h. Now, dm is rho pi y square dx, and to find out this integral, let us put the value of y from equation number 1. So, that will be 0 to h rho pi y square is r over h square x square whole square into dx. Okay. So, here rho pi and r square over h to the power 4, all of them are constant, let us take it outside, then we have 0 to h x to the power 4 dx, and that will be equal to 1 by 5 rho pi r square h. Let us call this equation number 2, this we can use to convert rho to m. Okay. Now, the moment of inertia of this thin disc about the x axis will be half dm y square, because dm is the mass of this disc and y is its radius, and the x axis passes through its center and perpendicular to the disc. So, therefore, it will be half dm y square. Let us put the value of dm. So, it is 0 to h half dm, dm is rho dx pi y square into y square. Okay. Now, we have to integrate this with respect to x. So, therefore, let us put the value of y also. So, that will be half rho pi, these are constant, 0 to h, and y is r over h square x square. So, we have r over h square x square to the power 4 dx. Okay. And this comes out to be 1 by 18 rho pi r to the power 4 h. Okay. Now, we can put the value of rho from equation number 2. So, from 2 we get Ixx equal to 5 divided by 18 m r square. Okay. Now, let us find out the moment of inertia about the y axis. So, I y y. For that, we can first write down the moment of inertia about this axis and then use the parallel axis theorem to find out the moment of inertia about the y axis. Okay. So, the moment of inertia about the diameter is equal to integral 1 by 4 dm y square, and then we can use the parallel axis theorem. So, plus x square dm, again it comes from the parallel axis theorem. Okay. So, now we have to just put the values. So, we have integral dm, I can take outside 1 by 4, and then y, the value of y is r over h square x square. So, r over h square x square to the power 2 plus x square dm. Now, let us put the value of dm also. So, we have 0 to h rho pi dm, dm will be rho pi dx y square. So, rho pi dx, and dx let me write down here, and then y square, y is r over h square x square whole square into 1 by 4 r over h square x square whole square plus x square dx. Okay. So, this I can rewrite as rho pi r square over h to the power 4, all of them are constant, limit 0 to h, r square over 4 h to the power 4 x to the power 8 plus x to the power 6 dx. Okay. And this is equal to rho pi r square over h to the power 4 r square over 4 h to the power 4 x to the power 9 divide by 9 plus x to the power 7 divide by 7, and we have to put the limit from 0 to h. So, that comes out to be rho pi r square h r to the power 2 divide by 36 plus h square divide by 7, and we can put the value of rho here. So, rho was from equation number 2 5 m divided by pi r square h. So, this comes out to be 5 m r square over 36 plus h square divided by 7. Now, let me give you a homework problem. And the statement is following: develop an expression for the mass moment of inertia of the homogeneous solid of revolution of mass m about the x axis, and the equation is given. Equation is y equal to k x to the power 1 by n. Okay. Its answer is I x x will be 1 by 2, 2 plus n divided by 4 plus n into m a square. Okay. So, you can take it as a homework problem, and you can find out the moment of inertia about x axis, and it will be this. Now, let us say if n is equal to 1, in that case this equation becomes y equal to k x, and the moment of inertia about the x axis for this case I x x will be half 2 plus 1 divided by 4 plus 1 into m a square, and this is equal to 3 by 10 m a square. Okay. This was our second problem. So, in the second problem we find out the moment of inertia for a structure which is made by revolving y equal to k x about the x axis. So, here the moment of inertia about the x axis was 3 by 10 m a square. This is exactly what we have. Now, let us look at the case if n is equal to half. In that case the equation becomes y equal to k x square. This was our third problem. So, herein I have y equal to k x square, and the moment of inertia about the x axis was 5 by 18 m r square. So, let us see that. Let us put n equal to half in equation number 1. So, I have I x x equal to half 2 plus half divided by 4 plus half m r square, and this becomes 1 by 2 5 by 9 m r square. So, here a is r. Okay. So, that is equal to 5 by 18 m r square. This is exactly what we got when the equation was k x square. With this, let me stop here. See you in the next class. Thank you.